get started with the next talk of the session. So this talk is by Matthias, who will be telling us about kind of a new semantics approach to probabilistic programming. This is one of the distinguished papers of Popple, so we're looking forward to it.
Thanks. My name is Matthias Vacker, and I recently joined the Stan team as a postdoc and programmer working on the compiler of the language that Maria just talked about. And today I'm going to be talking about some joint work with Ohad Kamar and Sam Staten when I was at Oxford working on the mathematical foundations of this sort of probabilistic programming language. So just for the people who came in for this session, very briefly say what a probabilistic programming language is. I'm talking here about statistical probabilistic programming languages. So these are languages that you use to specify statistical models. The idea is that the compiler then includes some complicated Bayesian inference algorithms that let you perform inference in your model. But the programmer only has to specify the model and doesn't have to worry about the inference. So that's the idea. These languages allow domain experts to put their expertise into a probabilistic model, and then the compiler does the complicated math, basically. Right. So the idea is, semantically, a program written in one of these statistical probabilistic programming languages represents a kind of unnormalized joint probability distribution over both the data we observe and the parameters that you're trying to infer. And the idea of the inference engine in the compiler is that it calculates a kind of normalization. Namely, it calculates the posterior distribution from this joint distribution, which amounts to a kind of normalization. Right, so that's sort of the semantics of these languages, roughly. But it turns out that if you look at the language features we find in the actual languages, this hand-wavy story about distributions takes quite a lot of effort to make precise. And that's what this paper is about, making that precise. So what sort of language features do we find in these languages? Well, first of all, we have continuous data types. And this is immediately obvious because even simple statistical models include normal distributions or other continuous distributions. So that off the bat makes the math a whole lot harder. Then we have two computational effects that we use to specify these probability distributions that make these languages go beyond ordinary functional languages. So one you're probably very familiar with, and it's just sampling or drawing random numbers. So here we have a sampling construct. Sample mu sigma that draws a random number from a normal distribution with mean mu and standard deviation sigma. The other construct you're probably not so familiar with. It's called, we call it scoring, and it amounts to, we can score with a real number, and what it does semantically is it reweights a probability distribution with a real number R. And that construct is what's going to make these distributions become unnormalized. And so let's look at a concrete example of a very simple program here on the bottom right, where we have a normal prior. We draw x from a normal prior using the sample construct. And then we have three observations from a normal likelihood. And we return the resulting distribution over x, which is the unnormalized posterior. So that would be the semantics of this program. So here we see that sampling is often used to specify the prior, while scoring is often used to specify the likelihood, or that we use it to condition on data. Because once we run inference and we normalize this distribution, the sort of reweighting becomes conditioning. Right. Now, when I was working on the Stan compiler recently, I was trying to implement some static analyses, and the first thing you run into is you'd really like lines in your program to commute. It just makes your life so much easier. And the thing is, that sort of seems possible in probabilistic programming languages. In fact, everyone assumes that it's possible when reasoning about these languages. And the reason they assume that, I can explain to you very easily. It's that once you think about the semantics of a let construct in one of these languages, it becomes obvious that it's a sort of integral. So then commutativity, or reordering lines of code, amounts to the Fubini theorem for reordering integrals. At least that's what happens if we're in a first-order language just working with probability distributions. We know that the Fubini theorem holds there. Now, things already become a lot harder if we go to to unnormalized distributions. And that's because we need to find a good class of unnormalized distributions. So we know that the Fubini theorem also holds for so-called sigma finite distributions, but these don't compose. That's a problem if we want to give semantics to a language. We also know that the theorem fails for arbitrary distributions. But Sam Staten recently identified this class of S-finite distributions, which is the closure of sigma finite distributions under composition, as also satisfying this Fubini theorem. So we are going to try to work with these S-finite distributions, except now we need to generalize them to language features that we have in some of the languages that we actually care about, namely higher order functions. Well, higher order functions we definitely want to have if we want to have a functional language. If we want to keep things functional, we don't have imperative constructs, so we definitely want map or some higher order functions to structure our programs. This already brings us outside the scope of ordinary measure theory, as we'll see. We also want term recursion, because that's quite useful for specifying certain stochastic processes. So here I wrote down a simple example of a Gaussian random walk using recursion. And we also want type recursion in the sense of FPC, or maybe just the recursive types that you have in OCaml. And there are two reasons for that. One is in our POPL paper last year, we showed that you can use inductive types, which are slightly less general than these recursive types, to construct intermediate representations for probabilistic programs. And you can also do correctness proofs on that representation. And the other reason is that a lot of probabilistic programming languages that we find in the wild are dynamically typed. And we can simulate dynamic types with recursive types, for instance, by constructing this dynamic type here, where we take the fixed point over type variable alpha of either being a real value or a function from alpha to alpha. And note that alpha occurs both covariantly and contravariantly here. And that creates some difficulty. Right, so I said languages, there are some languages with these features that we're trying to understand. Concretely, some of these languages are Church, Anglican, WebPPL, and Venture. And the features that we're trying to model are the sampling construct, continuous data types, scoring, higher order functions, term recursion, type recursion, and the Fubini theorem, so commutativity. And people have been assuming that commutativity holds. It's been used in proofs for correctness of certain inference schemes, but really there was no proof at the level of generality of these languages that property holds at all. And that's part of the point of this paper, that we give one of these correct. Yeah, we proved that that theorem actually is valid. So that's a bit of a relief. So there's been a really long literature on modeling combinations of recursion and probability, and a lot of the work is very, very impressive and very hairy. So I couldn't possibly go into it all, but I can just highlight some options that you have. So you could try to just use sets and sub-probability distributions. The problem with that is you don't get continuous data types. You could use measurable spaces. Then you don't have Cartesian closure, so you don't have higher order functions. Jones and Plotkin had some heroic work using cpos and sub-probability distributions, and they could model type recursion and term recursion. But as far as I'm aware, no one's proved the Fubini theorem at their level of generality. But they could show that it holds once you restrict yourself to commutative domains, to continuous domains. But the problem there is that that category is not Cartesian closed. So this started a whole search summarized by Jung and Tix for a Cartesian closed category of continuous domains with a commutative probability monad. Well, we're not quite solving that problem because we don't give a category of continuous domains, but we are modeling all these language features that we're asking for. Otherwise, I guess S-finite distributions allow you to model scoring. There was recent work on quasi-Borel spaces that allows you to do higher order functions. Then there was some really impressive recent work by Erhard Pagani and Tasson on probabilistic coherent spaces and measurable cones. They gave two different models, one of which can can do type recursion, but no continuous data types, and the other one can do continuous data types, but it's, again, not known whether type recursion or Fubini hold. Right. So the contribution of this paper is to give a category of quasi-Borel predomains with a commutative probabilistic power domain on it, as well as an axiomatic treatment of both measure theory and domain theory. And the fact that this treatment is axiomatic, I think, makes the semantics easier to use, as we demonstrated in our POPL paper last year, because it means you don't always have to understand all the details of the semantics, but you can work axiomatically. And finally, we show that you can interpret a probabilistic programming language with recursive types, and one of these languages that is untyped in our setting, and you can do so adequately. So that means you can use the semantics to prove valid program equivalences. So the untyped statistical lambda calculus that I mentioned here is like an idealized version of these languages that you see in practice. So now I'll briefly say something about the category of quasi-Borel predomains and our probabilistic power domain. So the challenge of the Young-Tix problem was to find a Cartesian closed category of continuous domains with, I guess, a power domain that satisfies Fubini. And the traditional approach is to start from the domain, take the open sets, the Scott open sets, take the Borel sets generated by those, and then take probability distributions or valuations on those. So you see that the domain structure and the measure theoretic structure are sort of the same. What's different about our approach, and I think why we avoid some of the difficulties that some of the other approaches faced, is because we keep the domain theoretic structure and the measure theoretic structure separate, but compatible. And specifically, the measure theoretic structure is going to be a quasi-Borel space structure, because we want higher order functions. Right, so what is a quasi-Borel predomain? It is a set with a partial order and a set of functions from the reals into our set that we call random elements. The partial order has to be an omega CPO, so we can take lubs of omega chains. The random elements have to form a quasi-Borel space, so that means that constant functions are random elements. We can measurably rearrange random elements with measurable functions from the reals to the reals. We can take measurable countable case distinctions of random elements, and we're still a random element. And on top of this, we put just one compatibility condition between the domain structure and the quasi-Borel space structure. And that is that if we have a pointwise omega chain of random elements, we can take the pointwise supremum, and we're still a random element. Okay. The morphisms in our category are just going to be Scott continuous functions that send random elements to random elements. So this is quite a simple category. It's complete, co-complete, Cartesian closed. It's very well behaved, easy to work with, I think. But I'll keep it concrete here, and I'll just give you some examples of omega quasi-Borel spaces. So you can take any measurable space, endowed with the flat order, and take as random elements the measurable functions from the reals into your space. And that gives you a quasi-Borel predomain. So in particular, the flat reals are one of these spaces, and we use that as our space of real values. Another example is if we start from an omega CPO, we can keep the order structure, and we can derive a set of random elements by taking measurable step functions and then taking suprema of omega chains. So in particular, if we start with the extended positive reals with their linear order, then because of the approximation by simple functions result in measure theory, the random elements just become the ordinary measurable functions. So this will be our space. This L space here will become our space of weights. And note that it is linearly ordered. That's, yeah. Another construction we have is a sort of lifting monad. So we can join a new bottom element, an undefined element to our domain, and then the random elements have to be undefined on a measurable subset. That's the idea. Right. So now we're in a position where we can define our probability monad. At least I'll try to convey the intuition. The details are in the paper. But really, it relies on two pretty old ideas. There's nothing too new here, except for the combination of these ideas. The first idea is an idea going back all the way to Schwartz, the idea of Schwartz distributions. And that idea is that you can interpret a distribution as an expectation operator. So as an element of this continuation monad. A distribution on X can be seen as a function that sends functions from X into the positive reals to a positive real number. Right? That's insight number one. Insight number two is the so-called randomization theorem, which says that well-behaved distributions on well-behaved spaces, let's say, arise as a push forward of the Lebesgue measure along some measurable function. And Luc Ong and I recently generalized that to S-finite measures. And so we're going to use that to say, well, OK, which submonad, which elements of this continuation monad are going to be valid distributions? Well, they're going to be the ones that arise as the push forward of the Lebesgue measure along one of these partial random elements, so the ones that have a randomization. So the push forward here is we take some randomization, and we take a function we want to integrate, and then we can take this integral. That's this map here. So really, we built our probabilistic power domain as a submonad of the continuation monad. That's going to be the trick. And we do it in such a way that we get a commutative monad, and the reason for the commutativity is just that the Lebesgue integral commutes. And all our elements ultimately come from the Lebesgue integral. So that's why things are commutative. Now, this monad has a lot of good properties. You can use it in recursive domain equations. It's commutative. Importantly, it satisfies the rules of syntactic measure theory, if that means anything to you. But it means you can interpret an integral calculus in this category and port proofs from traditional measure theory. And importantly, when we have a standard Borel space, it reduces to just ordinary valuations, and in this case, S-finite valuations. So that's a connection with some of the more traditional probabilistic power domains. So to summarize, presented a category of quasi-Borel predomains with a commutative probabilistic power domain of unnormalized S-finite distributions. We give an axiomatic treatment of measure theory and domain theory in this category. We adequately interpret probabilistic programming languages with recursive types and ones that are untyped, which allows us to prove valid program equivalences about these languages. And if you go look at the paper, you can find all kinds of details about how we do the axiomatic domain theory. We give an operational semantics similar to the great Bergström paper. And we give 4 different ways of characterizing this category, which gives some sort of canonicity of this construction. So I think I'll stop there. Thank you.
All right, thanks a lot. It's a very nice talk. If there's any questions, please come to the front, and you can ask in person or ask on Slido. I guess I'd start with one quick question. So you mentioned that you wanted to have this commutativity condition to interpret, swapping let bindings. Mm-hmm. Have you considered kind of other kind of equational reasoning that one might want to do about programs, and can you comment on how easy or hard it is to reason using the semantics?
Right. I can comment maybe based on our experience last year's POPL work, where we were not using these quasi-Borel predomains, but we were just using ordinary quasi-Borel spaces, so the setting without recursion. There we could interpret a similar kind of syntactic measure theory in our monads, and that gives you all kinds of equational reasoning tools about integrals. It's really funny. Actually, Kock has a great paper, the 2012 paper, where he shows that you can reproduce a completely surprising amount of measure theory just from the rules of commutative monad with this one extra axiom here. And in fact, we used it to prove correct sequential Monte Carlo last year. To prove correct trace MCMC, you needed a little bit more structure in the category, but hopefully that would transfer here as well.
Okay. I just had one more quick question. The last speaker could please come up and set up. So I think one thing that's nice about this work is that it has a close connection to standard probability theory and measure theory. So a lot of the results there can already be kind of ported over in some sense. You don't have to reprove them. Can you comment a bit on like how much this transport could be done? You know, are there some theorems that you think are very difficult to port over, or have things mostly come over?
No, some things.
There's a lot of work there that would be.
Some things are very hard. For instance, the disintegration theorem I've not been able to prove in this setting. A Radon-Nikodym theorem you can prove, or I'm not sure about the quasi-Borel domain setting, but the quasi-Borel space setting at least could prove that. I suspect that some results at higher order types will become very hard, but maybe at first order types will be relatively doable, especially because if the order is discrete, we just get ordinary standard Borel spaces. So in a way, we're conservatively extending well-known settings.
Okay, great. There's no other questions? I think. Oh, one more question.
I just wonder, have you considered adding sort of name generation to the language to model things like, you know, the Chinese restaurant process, that sort of thing?
Right. Yeah, we have thought about it, but it seems very interesting, but no results yet.
Great. Let's thank the speaker again.